Hello guys, welcome to Physics Grad. This is day 8 of daily quantum mechanics, and in this video we are going to learn what do we mean by inner product and inner product spaces. So let's get started. So in this video we will see what is the definition of inner product and what do you mean by orthogonal vectors, what do you mean by norm of a vector, what do you mean by an orthonormal basis, and so on. So let's get started here. So before we go into what we mean by inner product, let's just come back to the example of arrows, which are basically special cases of vectors. So we have already seen that the concept of vectors is much more general than the special case of arrows. But for arrows, we have, if you have taken a elementary physics course before, you would have come across something known as the dot product, which is defined for arrows, and it is defined in the following way. So if you know the length of the arrow or the magnitude of the arrows, in this case the arrow A and arrow B, and the angle formed between the two arrows, the smaller angle, then we can calculate or define something known as the dot product as given by this expression. Also, by now you should be familiar with what we mean by components and bases, and since arrows are in 3 dimensions, we can express any arrow in 3 dimensions in terms of 3 linearly independent vectors, which we call as bases. And if we choose the basis to be along the x, y and z axis with unit norm or unit length, then we can express the two arrows A and B in this manner. Okay, so you must be familiar with this already. And once we know the components, then we define the dot product as the expression given here. Basically, we multiply the respective x, y, z component and add them. So this will be useful if you do not know what is the length of the vectors or the angle between the vectors beforehand. So if you just have the components, then this is the way we calculate the dot product. So all of this must be familiar to you already from just high school physics or pre-university physics. So why do we use this dot product? What's the point of even defining a dot product? What does it tell us? What is its use? So let us see. So the reason why we use dot product is because using the definition of dot product, we will be able to define what is the length of the arrow in this manner. Basically, we say that the length of the arrow, or we denote it as mod A, is basically given by square root of the dot product of the vector with itself. Okay, so that gives us the length. Similarly, we can find the angle between the arrows by using this expression of the which again uses the definition of dot product. So this is where the definition in terms of components will be useful, because if we know the components, now we can calculate the length of that vector and also the angle between two arrows using the definition of dot product, and this is where the dot product becomes useful. And we extensively use it when we want to calculate quantities based on force, torque, momentum, electric field, etc., that we have already come across in physics that we have studied in high school. So this is the main use of dot product, but this dot product has been defined only for the case of vectors, which can be represented as arrows. But since vectors are much more than that, mathematically speaking, there should be a way of extending this definition of dot product to any general vector that we have defined before. So that's where the inner product comes in. So since mathematically speaking, vectors are much more than arrows, so we should be able to generalize the notion of dot product for the case of a general vector as well. And this generalization, we can't randomly define any definition for the inner product. It should be such that it should satisfy some conditions. Okay, and what conditions are those? How do we make make up these conditions which are valid enough in order for us to define the definition of inner product. So to do that, we again see what are the conditions for the dot product. What does the definition of dot product imply? And let us see that now. So for the generalization to work, the conditions that uh, the, the definition of inner product must hold should obey the similar properties as that of the dot product. And what I mean by that is the following. So if you take the dot product, you can immediately see that if you take the dot product between A and B, then it is the same as taking the dot product with B and A. Similarly, the dot product of a vector with itself is going to return a number which is always greater than or equal to 0, and this property we call as the positive semi-definite property, and it will be 0 only if the vector itself is 0, okay, and this property is called the symmetry property. And if we take the dot product of a vector with the linear combination of two vectors, then the result can be also expressed as the linear combination of the dot product of the first vector with the respective two vectors, okay, and this is called the linear property. So these three properties hold because of the definition of the dot product, and we can easily verify these properties by using the definition. Once again, I have shown it for especially the property 3 because property 1 and 2 are more or less obvious. You can just go through this quickly. Alright, so the generalization of the dot product that we are going to come up with will be called the inner product, and that's where the name comes in, or it is also called as the scalar product. And since for a general vector I have already shown you how I am going to denote it. So this is a vector with name v. So for any two vectors v and w, we denote the inner product of the two vectors as given by this symbol, okay. So we basically write a symbol like this and we put in the name of the vectors respectively, okay. So obviously, just like the dot product, this inner product, if it has to be the generalized version of the dot product, should return a number, but in our case it can be real or complex, okay. And for the generalization to work, as we have seen, it should also satisfy some properties which I have listed down here, which are slightly different as compared to the dot product. This is because we also have to deal with complex numbers, whereas in the dot product we always deal with the real numbers, okay. So to ensure that we take care of this possibility that we can get a complex number as a result when we take the inner product, the inner product must satisfy these three properties which are analogous to the dot product. So the immediate difference that you can see is that in this case there is complex conjugation when you invert the order in which you take the inner product. And the reason why we have this condition is because when you take the inner product of a vector with itself, it should always return a real number, because we will see that later on we interpret this quantity or the square root of this quantity as the length or norm of that vector, and that length or norm must always be a real quantity. And for that to happen, you should always ensure that in order to get the real number, this condition must be true, okay, and we will see with some examples in the next video as well, which will make it more clear. So if we look at the comparison of the properties between the inner product and the dot product, this is what we have. So we have the notation for the dot product as shown, a dot b, and this is the corresponding notation for the inner product, and there is the symmetry property for the case of dot product, whereas for the inner product we note that it is the skew symmetric property, and this is what makes the inner product a generalized version of the dot product, because here if you replace the vectors with arrows you will get back this result, okay. But note that I have not yet defined so for the dot product I had defined you how we calculate, if we know the components, how do we calculate the number uh, by the definition of dot product, but I have not yet told how we calculate this number, and we will see that in the next video. Okay, but now we just see why inner product is the generalized version of the dot product by just listing down what properties this inner product should also satisfy for us to say that this is the generalized version of the dot product. And the dot product of a vector with itself should be greater than or equal to 0, which is the positive semi-definiteness property, and the same should hold true for the case of inner product as well. And this is ensured because we have a complex conjugation here, because if this number were to return a complex number, then if we invert it, we will get its complex conjugate, and if you take this one, this should be equal to v complex conjugate, because if we invert it we get the same thing, and this can only happen only if these two quantities are real. Okay, so this ensures that this property ensures that the inner product of a vector with itself is always real, and this is useful because we can later on use this property to define the norm of the vector, which as we will see soon. And this is again the linearity property for the inner product when you take the linear combination on the right hand side, whereas because of the first property, if you take this linear combination on the left hand side, this is what you get. You do not get the same result as here, but you get a complex conjugation for the coefficients of the two vectors under linear combination. And this happens because of the first property, because if you take this inner product and if you invert it, then you should have a complex conjugation because of the first property. Now you take out these constants, oh I missed a b here, this constant out, then the a must get complex conjugated, b must get complex conjugated, and inverting this back you get this result. And as you can see, if you take linear combination in the left side of the inner product, you get an anti-linear result, okay, which is not the case in the case of dot product. So that's why I say that dot product is the special case of inner product when we consider the example of arrows as vectors. But for a more general vector which can be defined over a complex field, we have to stick with the inner product in order to calculate quantities such as the norm, or whether two vectors are orthonormal to each other and so on, okay, or orthogonal to each other and so on. So so just like how dot product is used to define the length of the arrow and the angle between the arrows and whether the two arrows are perpendicular to each other or not, similarly we can use the notion of inner product to calculate the norm of a vector or whether two vectors are orthogonal to each other or not. So these terms I will define soon, and this is just a terminology. So first of all, if you have a vector space and on top of it if you define the definition for the inner product for that particular type of vectors, then the vector space along with the definition of inner product will be called as the inner product space. Okay, so it's just terminology. So initially we just had the vector space V, and then for any two vectors V and W belonging to V, if we define how to calculate the inner product of V and W, then we say that the vector space V along with this definition forms the inner product space, I mean. Okay, so this is just terminology. And once we define what the inner product is or how to calculate the inner product, which I have not defined yet, which will be the topic for the next video, then we can define what we mean by orthogonal vectors, what we mean by norm of a vector, and what we mean by orthonormal basis and so on. So let's see what these things mean. So orthogonal vectors, if you compare it with arrows, are similar to perpendicular arrows. which means that they are independent of each other, as well as you cannot have component of one vector over the other vector. If you take the example of arrows, that's the analogy. Okay, so in dot product, or in the case of arrows, we say that the two arrows are perpendicular when their dot product becomes 0, because cos 90 is 0. So the generalization of this is basically the definition of orthogonal vectors, and we say that two vectors v and w are said to be orthogonal or perpendicular in the sense of arrows, okay, if and only if their inner product is 0. And remember, here there is no business of cos theta or the angle between the vectors, because these are not arrows, okay. So that's why this is the generalized version of two vectors being perpendicular. And this, so using this definition, we can find whether if the vector space consists of matrices, we can define if two matrices are orthogonal to each other or not, and so on. And this will be useful later on, as you will see. But for now, we just define these terms, and you should keep these things in mind. And norm of a vector is analogical to the length of the vector, length of the arrow, and that again we define as square root of the inner product of the vector with itself, just like in arrows we had square root of the dot product of the arrow with itself. Okay, and this we call as the norm, which is the generalized notion of length. Okay, so in this manner we will be able to define norm of a matrix. Okay, for example, set of all 3 cross 3 matrices form a vector space, and we can define the norm of each matrix using this definition. And this doesn't necessarily have to have an interpretation in 3 dimensions, right? Because okay, 3 cross 3 form 3-dimensional vector space, but if you take it depends on how you define the vector space, so we will see examples later on. Okay, anyways, so we say that a vector is said to be normalized if it has unit norm. This is similar to a unit vector that we are familiar with in the case of arrows. Okay, and an orthonormal basis, this is similar to the basis which we have considered, I, j, k, where basically each of the basis vectors have unit length or unit norm in the case of general vectors, and they are pairwise perpendicular or orthogonal in this case. Okay, so that's what we mean by orthonormal basis. So I think this should be close to 15 minutes, and I will stop with this. Thank you for watching. I will see you on day 9, where we will discuss the definition of how we define the inner product in terms of components, and we'll see some examples as well. So thank you for watching. Stay safe. See you next time.